The wind cut different across the vast prairies of the Dakota Territory. Rowena Holloway learned that her first winter of 1884, when frost formed on her cabin floor and her water bucket froze solid by morning, she had built her cabin exactly the way every homesteader was told to build it. Tight log walls, stone fireplace, standard floor joists proven and trusted. By February, she had burned more cordwood than 2 families should need, and still the cold seeped through the floorboards. Across the territory, settlers were fighting the same losing battle in cabins built by the book. Neighbors laughed when Rowena started talking about Spanish tunnels under the floor. Over 2 years, Rowena quietly applied an ancient technique from her aunt's memories that kept her floor 45 degrees Fahrenheit warmer while using a third of the fuel. Now, I'll break down the exact steps and principles behind this forgotten system. What did Rowena understand about moving heat under a frontier cabin that every settler missed? The homestead claim stretched across 640 acres of stubborn prairie, where the wind never stopped and timber grew sparse along distant creek beds. Rowena Holloway had filed her papers in the spring of 1882, staking her future on land that promised fertile soil, but delivered thin topsoil over broken shale that split under the plow. The nearest neighbor lived 3 miles east, and the closest settlement with the general store sat 2 days' ride south, through country that turned treacherous when winter storms rolled down from the Black Hills. By October, Rowena had finished her cabin according to every manual and guide circulated among homesteaders throughout the Dakota Territory. The structure measured 16 feet by 24 feet, with walls built from local ponderosa pine logs, each piece carefully fitted and chinked with mud and prairie grass. She had positioned the stone fireplace on the gable end exactly as recommended, using field stone hauled from a creek bed 5 miles north. The floor consisted of split pine planks laid across sturdy joists that rested directly on low stone piers, creating the standard frontier cabin that had sheltered thousands of settlers across the vast plains. The first serious cold arrived in November, with temperatures dropping to minus 15 degrees Fahrenheit and staying there for days. Rowena fed her fireplace continuously burning cord after cord of precious ponderosa and juniper wood that she had spent weeks cutting and hauling. The fire roared, and the air near the hearth grew warm, but the heat rose straight up and out through the roof while the floor remained brutally cold. Every morning she woke to find frost coating the inside surfaces of her windows and ice forming in her water bucket, despite keeping the fire burning through the night. 3 miles east, her neighbor Silas Reed faced identical problems in a cabin built to the same specifications. Reed had constructed his floor joists slightly closer to the ground, and the repeated heating and cooling cycles caused his floorboards to warp and shrink, creating gaps that let cold air whistle up from below. The constant expansion and contraction made his timbers squeak and groan through the night, and by December his floor had developed a permanent bow that made walking across the cabin feel like crossing the deck of a ship. To the north, the widow Martha Klein struggled in her smaller cabin, where a single night of letting the fire die down too low resulted in frost covering her floor by dawn. She lost a week's worth of stored vegetables when they froze solid, and her bedding became damp from condensation that formed when warm air from the fire met the cold surfaces throughout the cabin. Klein burned through her winter wood supply by January and spent the remainder of the cold months burning furniture and floorboards to stay alive. These failures followed the same pattern across the territory. Settlers built their cabins exactly as instructed, positioned their heating sources where the manuals suggested, and still found themselves burning enormous quantities of scarce fuel, while enduring floors that remained as cold as the frozen ground outside. The accepted wisdom held that a simple fire inside the living space was sufficient, that heat would naturally warm the entire cabin. and that any additional complexity was unnecessary luxury, unsuited to frontier life. Rowena had grown up with different stories. Her aunt, Beatrice Hawthorne, had immigrated from a village near Segovia in the region of Castile, bringing memories of stone houses that stayed warm through mountain winters, using methods passed down for generations. As a boy, Rowena had listened to descriptions of houses where fire burned outside the main room, but heat traveled through channels beneath the floor, warming the living space from below. Her aunt called the system Gloria, explaining how it used less fuel than open fires while keeping floors warm enough to walk barefoot, even in the coldest weather. The stories had seemed like old country tales until Rowena experienced her first Dakota winter and recognized the fundamental flaw in frontier heating wisdom. Standard cabin design treated heat as something that simply filled the air, ignoring the reality that warm air rises and escapes, while cold surfaces draw heat away from anyone trying to live above them. Her aunt's stories described a different approach that captured heat and delivered it where people actually needed it most. When Rowena mentioned the possibility of building heating channels beneath her floor, the reaction from neighbors and local authorities was swift and dismissive. Silas Reed declared the idea foreign nonsense and warned that digging beneath the cabin floor would weaken the foundation and risk collapse. The homestead inspector who visited in late winter examined Rowena's standard cabin, pronounced it properly built, and laughed at suggestions for Spanish tunnels that would complicate a simple, proven design. Even the merchant who sold supplies in the nearest settlement scoffed at the notion of external fireplaces and underground channels, insisting that frontier life required simple solutions, not elaborate European contraptions that would waste time and materials. "A good stove inside your house is all any sensible woman needs," she declared, dismissing centuries of heating wisdom as impractical fancy work. But Rowena had spent 3 years before homesteading as a maintenance laborer for the Denver and Rio Grande Railroad, learning to work with brick and stone in remote locations where structures had to endure harsh weather with minimal maintenance. She understood masonry construction and recognized that the heating system her aunt described was not exotic decoration but practical engineering designed for conditions similar to those she now faced on the Dakota plains. The central conflict had crystallized through her first brutal winter. The accepted frontier wisdom that simple interior fires provided adequate heating had proven inadequate for true comfort or efficiency in the harsh environment of the high plains. Rowena possessed knowledge of an alternative approach that promised to solve the fundamental problems that plagued every cabin in the territory. But implementing that knowledge would require her to reject the established methods that every authority insisted were sufficient and proper for frontier life. Rowena began construction in late March of 1883, when the ground thawed enough to dig, and the spring runoff filled the creek beds with the field stone she would need. The Gloria system required completely rethinking the relationship between fire structure and living space. Instead of heat rising uselessly into the air, the system would capture hot gases from combustion and force them to travel horizontally beneath the floor, transferring their thermal energy to masonry mass that would then radiate warmth upward into the cabin for hours after the fire died down. The first challenge involved raising her existing floor to create the void space necessary for the heating channel. Rowena carefully removed her floorboards and extended each floor joist upward by adding 6 inches of height, using mortise and tenon joints reinforced with hand-forged iron brackets. This elevation served multiple purposes, beyond simply making room for the ductwork. The higher floor created an insulating air gap between the living space and the cold ground, while the additional height allowed proper slope for the heating channel to ensure hot gases would flow efficiently from firebox to chimney. Creating the channel itself required masonry skills Rowena had developed during her railroad work, but adapted to the specific requirements of the Gloria system. She excavated a trench 18 inches wide and 12 inches deep, that ran the full length of her cabin from the planned external firebox location on the south wall to the chimney position on the north end. The trench followed a carefully calculated slope of approximately 1 inch per every 4 feet of length, ensuring that hot gases would flow naturally through the channel without requiring mechanical assistance. The channel walls required materials that could withstand repeated heating and cooling cycles while retaining and slowly releasing thermal energy. Rowena hauled field stone from Willow Creek, selecting flat pieces of red sandstone that split cleanly and could be fitted together with minimal gaps. She mixed mortar using clay from the creek bed, combined with lime she purchased from a kiln operator 30 miles south, creating a binding agent that would flex slightly with temperature changes rather than cracking like pure clay or lime mortar. The actual construction of the channel walls demanded precision that went beyond typical frontier masonry work. Each stone had to be positioned to create smooth interior surfaces that would allow hot gases to flow without turbulence, while maximizing contact between the flowing heat and the masonry mass. Rowena built the walls 8 inches thick using larger stones for the exterior faces and filling the centers with smaller pieces in mortar. The interior surface of each wall was carefully smoothed and sealed to prevent heat loss through cracks or gaps. Above the stone walls, Rowena constructed an arched roof for the heating channel, using a technique she remembered from railroad bridge work. She built a temporary wooden form, then laid thin flat stones in an arch pattern, each piece supported by its neighbors, and locked in place with mortar joints. This arch design distributed the weight of the floorboards and furniture above, while creating the maximum interior space for hot gas flow. The arch also provided structural strength that allowed the channel to support heavy loads without cracking or settling. The most critical element was the connection points where the heating channel met the firebox and chimney. At the firebox end, Rowena created a throat opening 8 inches wide and 6 inches high-sized to create sufficient draft while preventing the rapid escape of heat that would waste fuel. The opening angled downward slightly to guide hot gases into the horizontal channel and prevent backdraft during windy conditions. At the chimney end, the channel connected to a vertical flue that Rowena built using the same red sandstone but with a different internal configuration. The chimney incorporated a series of baffles horizontal stone shelves that forced the cooling gases to change direction multiple times before escaping. These baffles extracted additional heat from the exhaust gases, transferring it to the chimney mass, which then radiated warmth into the cabin long after the fire ended. Support for the raised floor came from a series of masonry piers that Rowena positioned to distribute weight while accommodating the heating channel below. Each pier consisted of stacked field stone rising from below ground level to the height of the new floor joists. The piers nearest the heating channel incorporated special features hollowed centers that connected to smaller secondary channels branching off from the main duct. These subsidiary channels allowed some hot gases to circulate around the pier bases, warming additional masonry mass and extending the heated area beyond the main channel path. The system incorporated one innovation that Rowena developed specifically for frontier conditions. Rather than using the solid stone floor slabs common in Castilian Gloria installations, she designed a hybrid approach that combined the thermal mass benefits of masonry with the practical advantages of wooden floorboards. Directly above the heating channel, she laid a course of thin sandstone slabs that would absorb and slowly release heat. Above these stones, she installed her original wooden floorboards, creating a composite floor that provided thermal storage while remaining suitable for frontier furniture and daily use. Testing began in October when night temperatures first dropped below freezing. Rowena built a small fire in the external firebox using dry pine from her woodpile and monitored the system's performance. Hot gases entered the channel smoothly and traveled the full 15-foot length before exiting through the chimney. The stone surfaces grew warm to the touch within 20 minutes, and heat began radiating upward through the floor slabs and wooden boards above. The thermal performance exceeded her expectations. Where her original cabin floor had remained within a few degrees of the outdoor temperature, the Gloria heated floor maintained surface temperatures 20 to 25 degrees Fahrenheit warmer than the outside air. More importantly, this warmth persisted for hours after the fire died down, as the heated masonry mass slowly released its stored thermal energy into the living space above. Fuel efficiency proved equally impressive. Rowena found that burning 1.5 cords of wood per month through the Gloria system provided more consistent warmth than the 3 to 4 cords she had previously burned in her standard fireplace. The system's ability to extract and store heat from combustion gases meant that virtually no thermal energy escaped unused up the chimney. The external firebox represented a radical departure from every heating method used across the Dakota Territory. Instead of placing the fire source within the living space where it competed with occupants for oxygen and created dangerous drafts, Rowena constructed her combustion chamber outside the south wall of her cabin in a lean-to structure that isolated the burning process from her daily life while maximizing heat extraction efficiency. The firebox itself measured 2 feet square and 18 inches deep, built with the same red sandstone she had used for the Gloria channel, but configured differently to optimize combustion control. The interior walls sloped inward slightly toward the bottom, creating a funnel shape that concentrated heat while allowing complete combustion of even the smallest fuel materials. At the base, Rowena installed a floor made from railroad iron bars, spaced 1 inch apart, elevating the fuel bed above a shallow ash pit that provided airflow from below while collecting debris. The most innovative feature was the adjustable air control system Rowena designed. Using techniques adapted from railroad maintenance work, she fabricated a sliding iron damper that could restrict or open the air intake at the base of the firebox, allowing precise control over combustion rate. Above the fire, a hinged iron cover could partially close the top opening, creating a controlled environment where fuel burned slowly and completely, rather than flaring up and wasting heat through rapid combustion. This external placement solved multiple problems that plagued frontier heating. No smoke entered the living space, eliminating the constant battle against backdrafts during windy weather. The firebox could accommodate fuel materials that would create excessive smoke or debris if burned indoors, expanding the range of available fuel sources beyond the precious cordwood that settlers struggled to obtain in sufficient quantities. Rowena discovered that the controlled combustion environment of her external firebox could effectively burn materials that other settlers discarded as worthless. Pine needles collected in great quantities from the scattered ponderosa groves burned intensely when properly managed, but produced heavy resin smoke that made them unsuitable for indoor fires. In the external firebox, the smoke contributed to heat production while being safely vented away from the living area through the Gloria channel and chimney system. Dry brushwood presented another abundant fuel source ignored by conventional heating wisdom. The territory's sparse vegetation produced vast quantities of dead branches, tumbleweeds, and scrub oak that accumulated in ravines and fence lines. These materials burned rapidly in open fires, creating brief, intense heat, followed by quick burnout that wasted most of their energy potential. In Rowena's controlled system, the same brushwood could be made to burn slowly and steadily, releasing its heat over hours rather than minutes. Pine cones represented perhaps the most overlooked fuel resource on the high plains. The scattered ponderosa and lodgepole pines dropped enormous quantities of cones each fall, creating piles of resin-rich organic matter that settlers typically raked aside or burned in waste fires. Rowena found that pine cones burned exceptionally well in her controlled system, producing intense heat with minimal ash, while consuming completely when given adequate airflow control. The combustion management technique required understanding principles that went beyond simply lighting fires. Rowena learned to load her firebox in layers with fine materials like pine needles at the bottom to establish initial heat followed by brushwood to maintain steady burning, and finally larger pieces like pine cones or small branches to provide sustained fuel. The key was controlling the air supply to maintain combustion at the optimal rate for heat extraction, rather than rapid fuel consumption. During a typical firing sequence, Rowena would open both the bottom damper and top cover fully, while lighting the initial fuel load, creating maximum airflow for quick ignition. Once the fire established itself and the heating channel began warming, she would partially close the top cover and reduce the bottom air supply, slowing the burn rate while maintaining sufficient heat production to keep gases flowing through the Gloria system. The timing of this combustion control proved critical to system efficiency. Too much air produced rapid burning that sent most heat up the chimney before the masonry could absorb it. Too little air caused incomplete combustion and excessive smoke that could clog the heating channel. Rowena developed a technique of monitoring the temperature of the stones around the channel entrance, adjusting airflow to maintain steady heat without overheating the masonry or wasting fuel through excessive draft. One crucial discovery emerged during her first winter of operation. The external firebox location allowed her to tend the fire without entering the heated living space, preventing heat loss through open doors and eliminating the indoor air disturbance caused by feeding fires within the cabin. She could load fuel, adjust dampers, and clean ash without affecting the stable thermal environment she had created inside her home. The fuel preparation process became a year-round activity, rather than the seasonal woodcutting that occupied most settlers. Rowena collected pine needles throughout the summer, storing them in the lean-to structure where they dried completely and remained readily available. Brushwood gathering occurred during her regular activities around the homestead, requiring no special expeditions to distant timber sources. Pine cone collection happened naturally during her other outdoor work, accumulating supplies that would last through extended cold periods. Testing during December of 1883 revealed the dramatic efficiency improvements this system provided. A typical firing using 2-bushel baskets of mixed small fuels pine needles, brushwood, and pine cones burned intensely for 30 minutes, then continued smoldering for another 2 hours under controlled airflow. The slow burn phase extracted maximum heat from the fuel while maintaining gas flow through the heating channel, warming the floor mass without requiring constant attention or fuel addition. The fuel consumption comparison with her neighbors proved startling. Where Silas Reed burned 6 cords of precious ponderosa logs during December, Rowena used materials equivalent to approximately 2 cords while achieving superior heating performance. Her floor remained warm enough for comfortable barefoot walking even on mornings when outside temperatures dropped to -20 degrees Fahrenheit, while Reed continued struggling with floors that barely rose above freezing despite continuous wood burning. Perhaps most significantly, Rowena's floor surface temperatures measured by pressing the thermometer bulb directly against the floorboards registered between 40 and 45 degrees Fahrenheit throughout the cold snap. This meant that her living space remained not just habitable but genuinely comfortable, allowing her to walk barefoot, work at her table without heavy clothing, and sleep under normal bedding rather than the multiple layers of blankets and furs that her neighbors required for survival. Spring thaw of 1884 revealed problems that Rowena had not anticipated during her system's initial winter operation. As snowmelt saturated the ground around her cabin and temperatures fluctuated daily between freezing and 40 degrees Fahrenheit, moisture began accumulating in the void space beneath her raised floor. The heated masonry had created a microclimate that attracted condensation, and without proper air circulation, this moisture threatened to undermine everything she had accomplished. The first sign of trouble appeared as a musty odor rising through her floorboards in early April. When Rowena removed several boards to investigate, she discovered droplets of water clinging to the underside of her floor and pooling in low spots of the Gloria channel. The problem stemmed from the temperature differential between the heated masonry mass and the cooling spring air creating conditions similar to those inside a root cellar where warm, moist air condensed on cooler surfaces. More concerning was the discovery that her carefully mortared channel joints had developed hairline cracks, where repeated heating and cooling cycles had caused thermal expansion and contraction. These tiny fissures allowed moisture to penetrate the masonry structure and created pathways for potentially dangerous gases to seep backward from the heating system into her living space during periods when the firebox was not operating. Rowena recognized that her Gloria system needed active ventilation to function safely, year-round, not just during the heating season. The solution required understanding principles of air movement that went beyond simple combustion draft. She needed to create controlled airflow that would remove excess moisture during spring and summer, while providing cooling circulation that could make her cabin comfortable during the brutal heat of Dakota's high-elevation summers. The ventilation system she designed incorporated elements from both Roman hypocaust technology and practical frontier construction. Rowena installed 2 vertical clay tile flues that connected to the Gloria channel at points approximately 5 feet from each end. These flues rose through the cabin walls and extended 18 inches above the roof line, creating natural draft that would continuously draw air through the underfloor space even when no fire was burning. Each ventilation flue measured 4 inches in internal diameter sized to provide adequate airflow without creating excessive heat loss during winter operation. The clay tiles came from a pottery works in Denver, transported by railroad, and then hauled to her homestead by wagon. Rowena joined the tiles with the same clay-lime mortar she used for the Gloria channel, ensuring that the ventilation system would expand and contract with temperature changes without developing leaks. The key innovation was a seasonal damper system that allowed Rowena to control airflow through these ventilation flues depending on weather conditions. During winter heating season, she could partially close dampers in each flue to prevent excessive heat loss, while maintaining enough airflow to remove any moisture that might accumulate. During summer months, she could open the dampers fully and also open a larger vent at floor level, creating a cooling system that drew hot air out of her cabin and pulled cooler air up through the Gloria channel from beneath the floor. Sealing the masonry against moisture infiltration required developing a mortar mixture specifically formulated for the thermal cycling that the Gloria system created. Rowena's original clay-lime mortar had proven adequate for construction, but lacked the flexibility needed for long-term durability under repeated heating and cooling. She experimented with different ratios of clay-lime and sand, finally settling on a mixture that incorporated chopped grass fibers as a binding agent that allowed the mortar to flex slightly without cracking. The improved mortar consisted of 3 parts: clay from Willow Creek, 2 parts lime, 1 part coarse sand, and chopped buffalo grass that she gathered from nearby prairie areas. The grass fibers, cut to lengths of approximately 1 inch, distributed throughout the mortar matrix and created microscopic reinforcement that prevented thermal stress from developing into visible cracks. This biocomposite approach drew on construction techniques that Rowena remembered from descriptions of adobe buildings in her aunt's Spanish village. Application of resealing work required carefully cleaning out the old mortar from channel joints and applying the new mixture during moderate weather when temperatures remained stable for several days. Rowena worked systematically through her entire system, paying particular attention to the connections between the horizontal channel and the vertical chimney and ventilation flues where thermal stress was greatest. The summer cooling capability transformed her cabin's livability during the intense heat that characterized Dakota's high-elevation summers. When outside temperatures reached 90 degrees Fahrenheit or higher, Rowena could open the floor-level vent and fully open the ventilation flue dampers, creating airflow that drew hot air out of her living space and replaced it with cooler air that had been in contact with the thermal mass of her Gloria channel and the earth beneath her cabin. This natural cooling system worked on the same principles as the Spanish courtyards, and thick-walled buildings that her aunt had described from Castile, where thermal mass and controlled airflow created comfortable interior conditions without requiring any mechanical assistance. The masonry that stored heat during winter became a cooling resource during summer, absorbing heat from the incoming air and releasing it gradually through the ventilation system. Testing during the summer of 1884 proved the system's effectiveness beyond winter heating alone. While neighboring cabins became virtually uninhabitable during the hottest days, with interior temperatures often exceeding outside air by 10 to 15 degrees Fahrenheit. Due to solar heating of walls and roofs, Rowena's cabin remained consistently cooler than the outside temperature. The thermal mass effect combined with controlled ventilation kept her interior approximately 12 degrees Fahrenheit, cooler than the outdoor air during peak afternoon heat. The moisture control proved equally successful. Throughout the spring thaw and into the humid conditions of summer thunderstorm season, Rowena's underfloor space remained dry and free of the mold problems that plagued many frontier buildings constructed directly on the ground. The continuous gentle airflow through her ventilation system removed excess humidity before it could condense and create problems with structural timber or stored goods. By autumn of 1884, Rowena had created a true four-season environmental control system that provided heating, cooling, moisture control, and ventilation using only natural forces and traditional masonry, thermal mass principles. The winter of 1885 to 1886 arrived with unprecedented severity across the Dakota Territory. By mid-January, a high-pressure system had settled over the plains, creating conditions that local weather observers would later record as the most sustained cold period in territorial history. Night temperatures plummeted to minus 25 degrees Fahrenheit and remained there for days at a time, while daytime highs struggled to reach 5 degrees above zero, even during the clearest sunshine. The cold snap began on January the 15th and continued unbroken for 17 days, accompanied by winds that sustained 30-mile-per-hour speeds and created snowdrifts that blocked roads and isolated homesteads throughout the region. These conditions created the ultimate test for every heating system across the high plains, separating functional solutions from inadequate ones with life-or-death clarity that allowed no room for theoretical discussions or polite disagreements about heating philosophy. Silas Reed's struggle began within the first 3 days when his indoor fireplace, burning continuously day and night, failed to prevent ice from forming on his cabin walls. His floorboards contracted so severely in the cold that gaps opened between them, creating channels for frigid air to flow upward from the space beneath his cabin. By the end of the first week, Reed was burning through a full cord of precious ponderosa logs every single day, a consumption rate that would exhaust his entire winter wood supply. Before the cold snap ended, the widow, Martha Klein, faced even more desperate circumstances. Her smaller cabin and limited wood supply forced her to ration fuel, allowing her fire to burn down during the night to conserve logs for daytime heating. On the morning of January the 20th, she woke to find her water bucket frozen solid and frost covering every surface inside her cabin, including the blankets on her bed. The extreme cold had penetrated so thoroughly that her food stores began freezing, despite being kept near the fireplace, threatening her survival through the remainder of winter. 3 miles north, homesteader Tobias Shaw experienced the structural failure that Rowena had long predicted would result from extreme thermal cycling. Shaw's cabin, built with slightly green timber that had not fully seasoned, suffered catastrophic warping as the repeated heating and cooling cycles caused his floor joists to twist and his floorboards to buckle. By January the 25th, gaps between his floorboards had opened wide enough to lose small objects, and cold air rushed through these openings with such force that his fireplace could barely maintain temperatures above freezing, even while consuming enormous quantities of fuel. Rowena's response to the crisis demonstrated the full potential of her integrated Gloria system under extreme conditions. Each morning throughout the cold snap, She loaded her external firebox with approximately 3-bushel baskets of mixed small fuels, pine needles, dry brushwood, and pine cones that she had collected and stored throughout the previous year. The controlled combustion process she had perfected allowed this relatively modest fuel load to burn steadily for 8 to 10 hours, with the thermal mass of her heating channel storing and slowly releasing heat long after the flames died down. The temperature measurements Rowena recorded during this period revealed the dramatic performance advantage her system provided. Using a mercury thermometer positioned on her floor near the center of her cabin, she documented interior temperatures that remained consistently between 28 and 32 degrees Fahrenheit, even during the coldest nights when outside air dropped to minus 25 degrees. This 55-degree differential represented a level of thermal protection that none of her neighbors achieved despite burning 3 to 4 times as much fuel. More significantly, Rowena's floor surface temperatures measured by pressing the thermometer bulb directly against the floorboards registered between 40 and 45 degrees Fahrenheit throughout the cold snap. This meant that her living space remained not just habitable but genuinely comfortable, allowing her to walk barefoot, work at her table without heavy clothing, and sleep under normal bedding rather than the multiple layers of blankets and furs that her neighbors required for survival. The fuel consumption comparison provided stark evidence of the system's efficiency. Rowena's total fuel use during the 17-day cold snap amounted to approximately 51 bushel baskets of small materials, equivalent to roughly 2 cords of conventional firewood. Meanwhile, Silas Reed burned 8.5 cords of split logs. Martha Klein exhausted her entire remaining wood supply of 6 cords, and Tobias Shaw consumed 7 cords, while still suffering from inadequate heating and structural damage. The crisis reached its peak on January 28th, when Shaw arrived at Rowena's cabin seeking emergency shelter after his own heating system had failed completely. Shaw had run out of accessible firewood when drifting snow blocked the path to his woodpile, and his damaged floor allowed so much cold air infiltration that his cabin had become uninhabitable. Despite desperate efforts to maintain a fire using furniture and floorboards as fuel, this emergency demonstrated another crucial advantage of Rowena's system: its independence from large timber resources and its ability to function using materials that remained accessible even during severe weather. While her neighbors struggled to reach distant wood piles through deep snow and fought to split frozen logs with numbed hands, Rowena simply gathered pine needles and small branches from areas immediately around her cabin that the wind kept partially clear. The social impact of Rowena's success during the crisis marked the beginning of a fundamental shift in local attitudes toward heating technology. When Tobias Shaw spent 3 days recovering in Rowena's consistently warm cabin while his own structure remained uninhabitable, he experienced firsthand the comfort and reliability that the Gloria system provided. Shaw became the first neighbor to request detailed instruction in building his own underfloor heating channel. By early February, as the cold snap finally broke and normal winter temperatures returned, Silas Reed and Martha Klein also approached Rowena seeking guidance. Reed had calculated that his fuel consumption during the crisis would leave him short of heating supplies for the remainder of winter unless he adopted a more efficient system. Klein recognized that her survival during any future cold snaps depended on finding an alternative to her inadequate fireplace heating. The request for instruction marked a cultural turning point that extended beyond individual heating solutions. For 3 years, Rowena's Spanish tunnels had been dismissed as unnecessary foreign complexity, unsuited to practical frontier life. The extreme test of the 1885 to 1886 winter had provided undeniable proof that traditional European heating wisdom properly adapted to local conditions and materials offered superior performance to accepted American frontier methods. Word of Rowena's success spread throughout the region as neighbors shared stories of the dramatic differences in comfort fuel consumption and structural integrity they had witnessed during the crisis. Local carpenter Elias Grant, who had initially mocked the Gloria system as impractical fancy work, arrived in March requesting partnership in building similar installations for other homesteaders who had heard about Rowena's performance during the cold snap. The documentation of these results, recorded in letters sent to relatives in settled regions and in reports to territorial authorities, created the first written record of successful Hippocaust-style heating adaptation to American frontier conditions. These accounts would later influence territorial building recommendations and contribute to the gradual acceptance of masonry heating systems throughout the Rocky Mountain region. By 1890, survey records from the Territorial Land Office documented at least 12 homestead cabins in the immediate region that incorporated underfloor masonry heating channels based on Rowena's original design. The system had evolved from an individual experiment into a recognized regional building technique that offered proven advantages for settlers facing the extreme climate conditions of the Dakota High Plains. If you found this deep dive into frontier engineering fascinating and want to see more stories exploring lost historical techniques and unconventional solutions, be sure to subscribe to the channel. Don't miss our next exploration into early agricultural innovations.